Now let's continue thinking about this problem. So we talk about that to decide whether this $320 profit will be good enough to cover those costs that will occur taking away one pump, 8 hours of labor, and 13 feet of tubing. We need to use those shadow price of those resources. Okay, so when we take away one pump from that original resource pool, our total profit will decrease by $200. So you think about this. The shadow price of this pump constraint is $200. That means if you decrease the right-hand side of that constraint, which represents the availability of the pumps, then the total profit, which is the objective function value, will decrease by 200. Okay, and when you again take away 8 hours of labor from that original resource pool, what's the impact on your total profit? You look at the shadow price of the labors, and that's $16.67. If you take away 1 unit, representing decreasing the right-hand side of your labor constraint by 1, then your total profit will decrease by 16.67. Now, if you decrease by 8, then your total profit will decrease by 8 multiplied by 16.67. Okay, and then for the tubing's shadow price is 0. And if this 13 is within the allowable decrease of that tubing constraint, then this shadow price of 0 will hold. Okay, and also remember that this decrease of 1 and decrease of 8, they need to be within the allowable decrease of the two constraints shadow price too. Okay, so now if it's profitable to produce any, then we take the difference. Okay, so the 320 is how much we're going to add to the total profit by producing this new hot tub. But we're going to also decrease the original total profit by this much. So as a result, we are losing $13.33 per Typhoon Lagoon that we produce, because this total profit that we add by producing this new hot tub is not enough to cover those decrease to the total profit, because we take out those resources, and so we won't be able to produce the same amount of EcoSpots and hydroluxes, and the total profit will decrease. So we're losing less money. It's not profitable to produce any of this Typhoon Lagoon. Now, if we want to double check it, we would create a new model by adding this new decision variable x3 that represents the number of Typhoon Lagoon to produce to this model here. So in the objective function, we have the 320 multiplied by x3, and we also add the resource needed to produce this third type of hot tub into these 3 constraints and the non-negativity. Then we would implement it and solve. Then when you solve it, you will find the optimal solution suggests no Typhoon Lagoon to be produced, as what we predicted, because we're going to lose money by producing it. So we'd better just stay with the original solution. And if you look at the sensitivity report from this new model, you will see that here, the column, this Typhoon Lagoon has a reduced cost of negative 13. I reduced the decimal point, but if you increase it, it would be negative 13.33. Exactly the same as what we calculated here, this negative 13.33. Okay, so with this, we're going to talk about this reduced cost column. What does it mean? The reduced cost for each product equals its per unit marginal profit minus the per unit value of the resources it consumes, priced at their shadow prices. So the reduced cost is calculated the same way as when we analyzed whether it is profitable to produce this third type hot top. Okay, so we used the per unit marginal profit, which is 330, subtracting the per unit value of the resources, all priced at their shadow prices. Okay, for example, if we look at this negative 13 here, how we calculate it is this 320 subtract this $200, which is the shadow price of the first constraint, and because its decrease is 1, it's within allowable decrease, so the shadow price will hold. Okay, and subtracting the second resource priced at its shadow price, it's 16.67. It's this value here, and the allowable decrease of 8 is within the allowable decrease. Subtracting the 0, this shadow price here, multiply, that's 13 units, that's within allowable decrease. Okay, so this value here is this reduced cost. And in this table, it lists some of the situations. For example, when a problem is maximization, and when we see in the optimal solution, a decision variable is at its simple lower bound, meaning that if we say this decision variable need to be greater or equal to a certain value, and when the problem is solved, this decision variable equals to that value, then we know the reduced cost of that decision variable should be less than or equal to 0. So if you think about it, for maximization problems, when you solve the model, you always want to increase your objective function value, right? And if you think about this in the context of a production problem, if you want to maximize your total profit, then you want to produce those products that help increase your objective function value. Okay, but if a certain decision variable is at its simple lower bound, say we say this x1 need to be greater than or equal to 0, and when the problem is solved, this decision variable equals to be 0, then that must mean producing this product does not help increase the objective function value. So it must have a reduced cost of negative. And if we look at, for example, when a model is solved and a decision variable value is at its simple upper bound, okay, so that means we say x1 should be less than or equal to, say, 50. And when the problem is solved, that x equals to 50, we put the limit for it to stop increasing. So it hit that limit and cannot go above that. And for maximization problems, then that decision variable must have a positive reduced cost, meaning that if you keep increasing that decision variable's value, you're going to add to your objective function value. However, because of that one constraint that's limiting its upper bound, then that decision variable stopped at that simple upper bound value. So in a minimization problem would be the same. If you think about, just take one, for example, if a decision variable is at its upper bound, okay, so it means that the decision variable, when the problem is solved, you want to keep increasing that decision variable value, but it hit upper bound, so that's where it stopped. For minimization problems, we want to have decision variables to keep increasing their value only if they are going to help decrease your objective function value. So that means if a decision variable has negative reduced cost, every time you produce this product, it's going to decrease your cost. Okay, it's going to help decrease your objective function. Then you would just like to keep increasing the value of this decision variable until it hit a simple upper bound. That's limiting it to keep going up. So some key points to summarize from the shadow price reduced cost part. The shadow prices of resources equate the marginal value of the resources consumed with the marginal benefit of the goods being produced. And the resources in excess supply have a shadow price of 0. So here when we talk about this marginal benefit, we are saying that when you add this resource or when you reduce this resource, how much it's going to impact your objective function value, how much it's going to increase or decrease your objective function value. And if a resource is already in excess supply, then it's not going to have any impact on your objective function value. Thus, its shadow price is 0. And the reduced cost of a product is the difference between its marginal profit, so how much it's going to increase your objective function value, and the marginal value of the resources it consumes. So subtracting the resources priced at their shadow price. So we are mainly looking at the net increase or net decrease to your objective function value. Products whose marginal profits are less than the marginal value of the goods required for their production will not be produced in an optimal solution. Like the Typhoon Lagoon example, it's not going to be produced because the marginal profit of 320 is not good enough to cover the resources it consumes priced at their shadow price. And so if we look at this Typhoon Lagoon again, if instead of 8 units of labor, it now only requires 7 units of labor, will it be profitable to produce any? You see, this is related to analyzing changes in the constraint coefficients. If you recall, this 8 is used in that labor constraint as a coefficient, right? So we put 8x3 in that left-hand side of the constraint to make sure that the labor resource required need to be less than or equal to resource labor available. So this is the coefficient change. Now if we do the same math, we use the 320 subtract, so the pump remain to be just 1 and the shadow price is the same. And then for the labor, now it only requires 7 units. And the shadow price is still the same. Subtracting the tubing, still 0, 13 units of tubing. Then we are going to gain $3.31 for every 1 unit of Typhoon Lagoon that we're going to produce. Given that those units, okay, so those units of resources we're going to take away from the resource pool are within the allowable decrease of their shadow prices. Now, what is the maximum amount of labor Typhoon Lagoon could require and still be profitable? So now we look at 8, it's not profitable. And when we reduce the labor hours to 7, it is profitable. It's asking, so what's the maximum amount of labor hour this Typhoon Lagoon could require to make it profitable? So that means if we change this 7 to be just a variable, and solve it. So as long as this entire part is greater than or equal to 0, then it's profitable to produce it, right? So we will just use L3 to represent the unit of labor, the maximum value that we can have here in order to be profitable. So make the right-hand side greater than or equal to 0. So we find out that it's 7.2 units. Okay, so now the next thing I want to talk about is we talk about in the object function table, if we have a 0 here, in absence of degeneracy, alternate solutions exist. But what is degeneracy, and how do we know if our problem is degenerate or not? We'll need to look at the allowable increase and decrease of the constraints. If we see a 0 in this allowable increase or decrease 2 columns, okay, if there's 0 appearing anywhere in these 2 columns, then the problem is degenerate. Then the method that we use to detect the alternate solution will no longer hold. So if you're asked to see if there's alternative solution, you need to first look at if there's 0 in this allowable increase decrease of the constraint to make sure that the problem is not degenerate. So no 0 here. And then you would look at if there's a 0 here, then you can tell there are alternative solutions if there's a 0 here. So about the degeneracy, the allowable increase or allowable decrease on any constraint, the right-hand side, okay, is 0, is an indication of degeneracy. When a solution is degenerate, the method that we mentioned earlier for detecting alternate optimal solutions cannot be relied upon. So even if there's a 0 in the allowable increase and decrease for the objective function coefficients, we still cannot conclude that the alternate optimal solutions exist. The reduced cost for the changing cells may not be unique. Also, the objective function coefficient for changing cells must change by at least as much as, sometimes possibly more than, their respective reduced costs before the optimal solution would change. So what does that mean? When two people solve the problem and generate the sensitivity report, you may get two different set of values for the reduced cost for those decision variables. Okay, because they are not unique. Also, the objective function coefficient have their allowable increase and decrease ranges in which if the problem is not degenerate, then we can tell if the objective function coefficient change outside of those allowable increase and decrease range, then the solution will change for sure. However, when the problem is degenerate, the objective function coefficients may need to change more than their reduced cost before their optimal solution would change. Third, the allowable increases and decreases for the objective function coefficients will still hold. So that means if you change the objective function coefficients within those allowable increase and decrease, then you are sure the solution won't change. But if we change outside of the range, we cannot tell if the solution will change. So it says the coefficient may have to be changed beyond the allowable increase and decrease limit before the optimal solution changes. And the given shadow prices and their ranges may still be interpreted the usual way, but they may not be unique. So you can probably understand here because the reduced costs are closely related to the shadow prices. In the previous slide, we talked about when we have a problem being degenerate, the reduced cost may not be unique. So here, the shadow prices and their ranges may not be unique either. So when two people solve the problem and generate the sensitivity reports, you may have two sets of shadow prices with their allowable increase and decrease ranges, same as the reduced cost. So this means that a different set of shadow prices and ranges may also apply to the problem, even when that optimal solution is unique. With this, we covered every part of this sensitivity report in terms of what information it gives us and how to interpret those values. So the solver's sensitivity report answers questions about amounts by which the objective function coefficients can change without changing the optimal solution. The impact on the optimal objective function value given some changes in constrained resources, whether it's on the right-hand side representing the available amount of the resources or the left-hand side coefficients representing how many units of each resource that is required. The impact on the optimal objective function value of forced changes in decision variables. So the reduced cost part. Say if we have a negative 13 as the reduced cost of x3, then if we force that x3 to be equal to 1 from the current optimal value of 0, then we know that our objective function value will be decreasing 13. The reduced cost tells us the impact on the optimal objective function value if we force that decision variable to change. The impact on the optimal solution of changes in constraint coefficients. Besides the sensitivity report, solver generates two other reports. One is the answer report, and the answer report has three tables too. So the first one, again, it's the same as the sensitivity report. It gives you the final value of your objective function. And then the second one, it gives you the final value of your decision variables. So you can see the original value are when we started the model, they are 0. In some cases, they may be set at different value, but it will tell you what the final values, what the optimal values are. And then if you look at the constraints, it will list all the constraints, including the non-negativity constraints, and tell you whether a constraint is a binding constraint or not, and what's the slack. If you recall, when we use the simplex method, we would add a slack to a less than equal to constraint to convert it to a equal to constraint. And here the slack represents the difference between your left-hand side and your right-hand side. Okay, so for those two binding constraints, we have slacks of 0, representing their left-hand side value is the same as their right-hand side value when the model is solved. And then for those non-binding constraints, this is the difference between the left-hand side and right-hand side. And if you recall, for the tubing, we had 2,880 units available. And when the problem is solved, the left-hand side is 2,712. So that's the amount of tubing needed. And the difference between this and the right-hand side is the 168. And for these two constraints, the non-negativity constraint, because what we said is the x1 greater than or equal to 0. So when the x1 is solved, it equals to 122. So the difference between the left-hand side and the right-hand side, which is 0, is 122. Same as this next non-negativity constraint. And the limits report does not really tell you much thing besides the current value for your objective function and the decision variables. It basically tells you if you set one of the decision variable to be 0, what will be your objective function value.